The objective of this lecture is to provide a foundation of rigid body orientation using Euler angles. This lecture will be divided into the following parts. First, we will describe two commonly used Euler angle sequences. And these two commonly used sequences will be the 3-1-3 Euler angles. These are also known as spacecraft Euler angles. And then 3-2-1 Euler angles, which are known as aircraft Euler angles. Now, for each of these Euler angle sequences, we will determine the following. First, we will determine coordinate transformations. And second, we will determine the angular velocity. Now, because we're dealing with a rigid body, this is actually the angular velocity of a rigid body, and it's relative to an arbitrary reference frame. And these two parts actually go together in that the Euler angle sequences themselves require that the coordinate transformations be determined and also the angular velocity individually corresponding to each of the angles in the Euler angle sequence. So we're going to do all of this together for each Euler angle sequence. So we'll start with 3-1-3 Euler angles, and we'll do the entire derivation for 3-1-3, and then we'll repeat the process the second time around for 3-2-1 Euler angles. So let's start with the definition of Euler angles. So Euler angles are a way to parameterize the orientation of a rigid body. So Euler angles provide a way to parameterize the orientation of a rigid body. Now, in general, there are 12 Euler angle sequences. So there are 12 possible Euler angle sequences. And the most commonly used ones are what are known as 3-1-3 Euler angles and 3-2-1 Euler angles. And these Euler angles form what are called successive rotations. And they're also known as successive single-axis rotations. So they're single-axis rotations. What that means is that any rotation arises from an orientation where the previous rotation leaves off. So if I start by rotating about one axis, it's a single axis rotation, the next rotation starts where the previous rotation leaves off. And that continues for all three rotations. So every Euler angle sequence consists of three successive rotations. And maybe be a little bit clearer about that. Three successive single axis rotations. So as I said, we're going to do 3-1-3 Euler angles and 3-2-1. There are 12 possible Euler angle sequences. We're not going to do all 12 because many of them are not commonly used. The ones that are commonly used are these two, and so we're going to focus the rest of this lecture on these two Euler angle sequences. So the first Euler angle sequence that will be studied in this lecture is the sequence of 3-1-3 Euler angles. 3-1-3 Euler angles are defined as follows. The first rotation is by an angle called psi, and it's about the 3-axis, which is equivalently the z-axis. The second rotation is by an angle called theta, and it's about the new 1-axis, which is equivalently the new x-axis. The third rotation is by an angle called phi, or phi, and it's about the new 3-axis, or equivalently the new z-axis. Now, in order to be able to determine these rotations and quantify them, we need to determine reference frames that are associated with these rotations. In other words, reference frames that are fixed in each of these rotations. So we need 4 reference frames. Now, the first of these reference frames is the base reference frame, which is going to be called A. So this is the base reference frame. And what that means is that it's the reference frame from which all the rotations start. And it's going to have an associated basis, which will be called A1, A2, A3. The second reference frame is going to be called P. And P is the reference frame that results from the first rotation. By the angle psi. And it has a basis which will be called P1, P2, P3. The third reference frame is going to be called Q, and it results from the second rotation by the angle theta with basis Q1, Q2, Q3. And then the last frame is going to be called B, which is actually the final orientation, and it results from the third rotation by the angle phi with a basis B1, B2, B3. Now, the last basis, B1, B2, B3, is actually fixed in what would then be the rigid body. So B is the rigid body itself. In other words, we have now rotated the rigid body from its initial orientation, which would be frame A, through these 3 rotations to a new orientation, which gets us to reference frame B, which is the rigid body. Now, in order to be able to understand where this all goes, is that ultimately we want the following out of this, to come out of this Euler angle sequence, which is we want the coordinate transformations and we want the angular velocity omega BA. And this is going to be expressed in the body fixed basis B1, B2, B3. So now let's get started with each one of these rotations. In succession, I'm going to do each one of these rotations, and I'm going to draw 2-dimensional pictures because it's a lot easier to see what's going on in 2 dimensions than it is to see in one big 3-dimensional picture. So rotation 1 is about the 3-axis by the angle psi. So this rotation looks as follows. Using the bases I've defined already, I start with the basis A1, A2, and A3. I then rotate by the angle psi, resulting in the basis P1, P2, P3. So here's P1, here's P2, and then P3 is the same as A3, and this is the angle psi. Now using this diagram, I can write the basis vectors A1, A2, and A3 in terms of P1, P2, and P3. So A1 is going to equal cosine of psi times P1 minus the sine of psi times P2. A2 equals the sine of psi times P1 plus the cosine of psi times P2, and A3 is equal to P3. Now using the relationships between the basis vectors A1, A2, A3, and P1, P2, P3, I can develop the transformation from A to P. And we do this transformation, we compute it using the approach that was developed in an earlier lecture where we defined these direction cosine matrices. So remember that this transformation, the way I've written it, is from A to P if I read across each row and put those components down the column. So that means that the transformation from A to P is going to equal cosine of psi minus the sine of psi, 0, and then sine of psi, cosine of psi, and then 0, and then 0, 0, 1. Now the last thing I need is I need the angular velocity of P as viewed by an observer in frame A. And you'll notice that that angular velocity is equal to psi dot times P3. And again, I always write the angular velocity in terms of the basis fixed in the frame on the right. And the frame on the right in this angular velocity is P, so I write it in terms of the basis P1, P2, P3. So that's a full description of the first rotation. So moving on to the second rotation, rotation 2 is about the new one-axis by the angle theta. So here's what that rotation looks like. So where did we leave off? Well, we left off with this basis P1, P2, P3. But this rotation now takes place about the one axis because it's the second of the 3-1-3 Euler angle rotations. So this direction has to be P1. So completing the right-handed system, that makes this P2 and makes this P3 because P1 crossed with P2 is P3. So if I rotate by the angle theta, that results in this new basis, which is Q1, Q2, Q3. But since I'm rotating about P1, the basis vectors that actually change their locations or change their orientations are Q2 and Q3, while Q1 is the same thing as P1. So using this diagram, I can now express the basis vectors P1, P2, and P3 in terms of Q1, Q2, and Q3. So what do I get? I get that P1, P2, and P3. So P1 is equal to Q1. P2 is equal to cosine of theta times Q2 minus the sine of theta times Q3. And P3 is equal to sine of theta times Q2 plus the cosine of theta times Q3, which again, following the convention that was developed in the previous lecture, we now have the transformation from P to Q, which if I read across and put these down the columns, I get 1, 0, 0. I get 0 cosine of theta minus the sine of theta, and then I get 0 sine of theta, and then cosine of theta. And in a manner similar to what I did for the first rotation, the angular velocity of Q in P is equal to theta dot times Q1. So that completes the second rotation. So moving on to rotation 3. Rotation 3 is about the new 3-axis by the angle phi. So this picture, again, picks up where the previous picture left off. So what did I leave off at? Well, I left off with this basis Q. So now I'm doing a rotation about Q3 because it's a 3 rotation, which means that I have a similar picture to what I had at the very beginning. Q3 crossed with Q1 is Q2, and I wind up with this final basis, which is B1, B2, and B3. And this angle is phi, or phi. So going through the same process, we wind up with Q1 is equal to cosine of phi times B1 minus the sine of phi times B2. And then Q2 is equal to the sine of phi times B1 plus the cosine of phi times B2. And Q3 is equal to B3, which then results in a transformation from Q to B, which is equal to, and again, reading across and putting the columns down, we get cosine of phi minus the sine of phi, 0. We get sine of phi, cosine of phi, 0, and then 0, 0, 1. And then correspondingly, we get the angular velocity of B and Q equals phi dot times B3. So now we've defined all three rotations, the transformations between the frames, and we've figured out the angular velocities as well. So the next step is to determine the angular velocity of B relative to A. Now, why am I determining that? Well, it's again, let's recall, A is the base reference frame, and B is the rigid body. So omega BA is the angular velocity of the rigid body as viewed by an observer fixed in the base reference frame. So let's go ahead and compute this angular velocity. So we know that the angular velocity of B and A, and this is from the addition of angular velocities property, is equal to the angular velocity of P in A plus the angular velocity of Q in P plus the angular velocity of B in Q. We've determined all these angular velocities, so let's write them down. So we get psi dot times P3 plus theta dot times Q1 plus phi dot times B3. Notice 3-1-3. That's why it's called the 3-1-3 Euler angle sequence, because of the rotations. Now, in order to be able to do this in terms of the basis B1, B2, B3, we need to transform P3 to the basis B1, B2, B3, and we also need to transform Q1 to the basis B1, B2, B3. So in order to perform those transformations, let's write the angular velocity first and express everything in the coordinates in which everything is written here in terms of column vectors, and then we'll do the appropriate transformations. So then, the angular velocity of B and A expressed in coordinates fixed in B is equal to psi dot times P3 plus theta dot times Q1 plus phi dot times B3, the whole thing expressed in B, which is equal to psi dot times P3 expressed in B plus theta dot times Q1 expressed in B plus phi dot times B3 expressed in B. But P3 and Q1 are not expressed in B. So in order to be able to get this done correctly in terms of B, I need to write this as psi dot times the transformation from what to what? Well, it's the transformation from P to B times P3 expressed in P plus theta dot times the transformation from Q to B times Q1 expressed in Q plus phi dot, well, B3 is already expressed in B, and that expressed in B is just equal to 0, 0, 1. So now I have to get these transformation matrices, and I have to use them appropriately. So first, I know that the transformation from P to B is equal to the transformation, well, let's do this. It's the transformation from P to Q times the transformation from Q to B. So I need those two transformation matrices. Next, I know that the transformation from Q to B, this was already given. So we already have this. Already have. So we can now go about getting these two transformation matrices and multiply them together to get the transformation from P to B. So let's do that. So from earlier, the transformation from P to Q was equal to 1, 0, 0, 0 cosine theta minus the sine of theta, and 0 sine of theta cosine theta. And also, the transformation from Q to B is equal to, well, it's cosine of phi minus the sine of phi, 0, sine of phi, cosine of phi, 0, 0, 0, 1. So now let's use these two transformation matrices to compute the first term in this angular velocity expression that we have above. So then we have the transformation from P to B times P3 expressed in P is equal to the transformation from Q to B times the transformation from P to Q times 0, 0, 1, which is equal to cosine of phi minus the sine of phi, 0, sine of phi, cosine of phi, 0, 0, 0, 1, multiplied by 1, 0, 0, 0 cosine of theta minus the sine of theta, 0 sine of theta cosine of theta times 0, 0, 1, which is equal to cosine of phi minus the sine of phi, 0, sine of phi, cosine of phi, 0, 0, 0, 1, times, now when I take that last product over there, I get 0 sine of theta cosine of theta. It is multiplying that second matrix by 0, 0, 1. So then that in turn is equal to, I've got sine of phi, sine of theta, and then I have cosine of phi, sine of theta, and then I have cosine of theta. So next, CQ to B times Q1 expressed in Q is equal to cosine of phi minus the sine of phi, 0, sine of phi, cosine of phi, 0, 0, 0, 1, multiplied by 1, 0, 0, which is equal to, well, we get cosine of phi minus the sine of phi and 0. So now I can use these expressions and I can add them together with the angular rates that I had to get the angular velocity of B and A. So as a result, we have omega BA expressed in B is equal to psi dot times sine phi sine theta cosine phi sine theta and cosine theta plus theta dot times cosine of phi minus the sine of phi 0 and then plus phi dot times 0, 0, 1, which when added together give psi dot sine phi sine theta plus theta dot cosine of phi and then psi dot cosine of phi sine theta minus theta dot sine of phi and then psi dot cosine theta plus phi dot. So then writing omega BA in vector form gives omega BA is equal to psi dot sine phi sine theta plus theta dot cosine of phi, the whole thing times B1, plus psi dot cosine phi sine theta minus theta dot sine of phi times B2 plus psi dot cosine theta plus phi dot times B3. So that completes the description of 313 Euler angles, and next we will move on to 321 Euler angles. So now we describe 321 Euler angles. So the 321 Euler angles perform similarly to 313, except for the rotations are different. So the first rotation, and again the angles are named the same, psi, is about the 3-axis, which is equal to the z-axis. The second rotation, which is by the angle theta, is about the new 2-axis, which is equal to the y-axis. And then the third rotation, which is by the angle phi, is about the new 1-axis, which is equal to the x-axis. So similar to 313 Euler angles, we need 4 reference frames, and we're going to call these reference frames the same, with the same names that we did before, which is A is going to be the base reference frame, and it's going to have a basis A1, A2, A3, and then P is going to be the reference frame that results from the first rotation with basis P1, P2, P3, and then Q results from the second rotation, and it will have an associated basis Q1, Q2, Q3, and then finally we have the basis B, which is the rigid body itself. It results from the third rotation with basis B1, B2, B3, and of course B is the rigid body. And using this information, we are also going to determine the angular velocity of B in A expressed in the body fixed basis B1, B2, B3. So now let's go ahead and do these different rotations. So rotation 1 is about the 3-axis by the angle psi. So this rotation looks exactly the same as what it looked like in the 3-1-3 Euler angles because it's the same first rotation. So we start with A1, A2, and A3, and then we rotate about A3 equals P3 to get the basis P1, P2, and P3. So this angle is psi. So now we can go ahead and write down these relationships, which gives A1 is equal to cosine of psi P1 minus the sine of psi P2. A2 is equal to the sine of psi P1 plus the cosine of psi P2, and A3 is equal to P3, which results in the transformation from A to P equaling cosine of psi minus the sine of psi, 0, sine of psi, cosine of psi, 0, 0, 0, 1, and the angular velocity of P as viewed by an observer in frame A is psi dot times P3. And that's exactly the same as what we had in the 3-1-3 Euler angles. But now the second rotation is going to be different because the second rotation is going to be about the resulting 2-axis because it's a 3-2-1 Euler angle sequence. So let's do the second rotation now. So rotation 2 is about the new 2-axis by the angle theta. So this picture is going to look a little bit different, but we're going to draw it with the same schematic, but the vectors are going to be different. So now I'm doing a rotation about P2. So P2 crossed with P3 gives me P1, which then gives me that this basis that results from this rotation has to be Q3 and Q1 and then Q2, and this angle is theta. Now, given these relationships, I have that P1 is equal to, well, it's equal to cosine of theta times Q1 plus the sine of theta times Q3. P2 is equal to Q2, and then P3 is equal to minus the sine of theta times q1 plus the cosine of theta times q3. So then these relationships can be used to determine the transformation from P to Q, which is equal to cosine of theta 0 sine of theta 0 1 0, and then minus the sine of theta 0 cosine of theta. And finally, the angular velocity of Q in P, using the same approach that we used previously, is theta dot times Q2. That takes care of the second rotation. So now we do the third rotation. So rotation 3 is about the new one-axis by the angle phi. So let's draw this picture. So we have the result from the previous rotation, but now we're rotating about the one-axis. So this is Q1, and then this is Q2, and this is Q3. And then when we're done with this rotation, we wind up in the basis fixed in the rigid body. So this is B2, B3, and then B1. So that implies that Q1 is equal to B1. Q2 is equal to, let's add the angle phi into this diagram. So Q2 is equal to cosine of phi times B2 minus the sine of phi times B3. And then Q3 is equal to sine of phi times B2 plus cosine of phi times B3, which implies that the transformation from Q to B is equal to, so Q1 is equal to B1, so we get 1, 0, 0, and then we get cosine, we get 0 cosine of phi minus the sine of phi, and then we get 0 sine of phi cosine of phi. And then the angular velocity of B in Q is equal to phi dot times B1. So now we can put all this together to get the angular velocity of the rigid body as viewed by an observer in the base reference frame. So then the angular velocity of B in A is equal to psi dot times P3 plus theta dot times Q2 plus phi dot times B1. And now we go through a similar process that we did with 313 Euler angles to express everything in the body fixed coordinates. So we then have that the angular velocity of B in A expressed in body fixed coordinates is equal to this entire expression psi dot P3 plus theta dot Q2 plus phi dot B1, all expressed in body fixed coordinates, which is equal to psi dot P3 expressed in body fixed coordinates plus theta dot times Q2 expressed in body fixed coordinates plus phi dot times B1 expressed in body fixed coordinates. Well, B1 expressed in body fixed coordinates is just 1, 0, 0. So that one is not too complicated, but we need to deal with the other ones. So we get psi dot. Now, because I have P3 expressed in B, I need the transformation from P to B times P3 expressed in P plus theta dot times the transformation from Q to B times Q2 expressed in Q, and then plus phi dot, and as I said, this last one is just equal to 1, 0, 0. So now we can go ahead and we can perform the same transformations that we did previously, which is that the transformation from P to B times P3 expressed in P is equal to the transformation from Q to B times the transformation from P to Q times 0, 0, 1, which is equal to 1, 0, 0, 0 cosine of phi minus the sine of phi, 0 sine of phi cosine of phi times cosine of theta, 0 sine of theta, 0, 1, 0 times minus the sine of theta, 0 cosine of theta times 0, 0, 1. So then we obtain C P to B times P3 expressed in P is equal to 1, 0, 0, 0 cosine of phi minus the sine of phi, 0 sine of phi cosine of phi times minus the sine of theta, 0 cosine of theta, which is equal to, so we get minus the sine of theta, and then we get sine phi cosine theta, and then cosine of phi cosine of theta. So next, CQ to B times Q2 expressed in Q is equal to 1, 0, 0, 0 cosine of phi minus the sine of phi, 0 sine of phi cosine of phi times 0, 1, 0, which is equal to 0 cosine of phi minus the sine of phi. And now we can take these results and we can put them together to compute the angular velocity of B and A expressed in body fixed coordinates. So then the angular velocity of B and A expressed in body fixed coordinates is going to equal psi dot times, well, I've got CB to P times P3 and P, which gives me minus the sine of theta, sine of phi, cosine of theta, and cosine of phi, cosine of theta, plus theta dot times 0 cosine of phi minus the sine of phi plus phi dot times 1, 0, 0. So adding the components in the last expression gives omega BA expressed in B is equal to minus psi dot sine theta plus phi dot, psi dot sine phi cosine theta plus theta dot cosine of phi, and psi dot cosine of phi cosine theta minus theta dot sine of phi. So then, expressing omega BA in vector form gives omega BA is equal to minus psi dot sine theta plus phi dot times B1 plus psi dot sine phi cosine theta plus theta dot cosine of phi times B2 plus psi dot cosine of phi cosine of theta minus theta dot times the sine of phi times B3. So that takes us to the end of 3-2-1 Euler angles. Next, we are going to provide an overview of what's common to both Euler angle sequences, and actually what's common to essentially all Euler angle sequences, but in particular the two that we studied here. Now note that for both Euler angle sequences, for reference frames, and corresponding coordinate systems, were used. And these four coordinate systems led to 3 direction cosine matrices. And these direction cosine matrices were the transformation from P to A, the transformation from Q to P, and the transformation from B to Q. So as a result, we now actually have a way of being able to compute the transformation from the body fixed coordinates to the base reference frame. So suppose that W is an arbitrary vector. Then if I have W, I'm going to start here on the right and move my way to the left. If I have W expressed in B, so it's expressed in body fixed coordinates, I can express that vector W in the base reference coordinates, or the coordinates fixed in the base reference frame, using the transformation from B to A. But the transformation from B to A is equal to the transformation from P to A times the transformation from Q to P times the transformation from B to Q. Now, regardless of which Euler angle sequence I'm using, this same relationship holds, because I named the coordinate systems in the frames exactly the same way for either of these Euler angle sequences. So I went from A to P, P to Q, and Q to B, and those define the 3 rotations. So it doesn't make a difference. This is the relationship that provides me the transformation from B to A sequentially going through the different coordinate systems, or equivalently through the different frames, or yet again equivalently through all the rotations sequentially. And it starts with the last rotation and it works its way back. So when you do this multiplication, you have to do the multiplication on the left, starting with the last two frames and then working your way back through the transformations by multiplying on the left-hand side. So it goes from the last to the first. Because if you notice this expression I've got here, it says the vector W expressed in B has to be multiplied on the left by B to A to get the vector expressed in A. And all that amounts to is the following sequence of transformations. If you want to see it in steps, here's what it looks like in steps. So stepping more slowly, we have the following. That we said that the vector W expressed in A is equal to CB to A times the vector W expressed in B. But we know that W expressed in Q is equal to the transformation from B to Q times W expressed in B. And we know that W expressed in P is equal to the transformation from Q to P times W expressed in Q. And we know that W expressed in A is equal to the transformation from P to A times W expressed in P. So if I just work my way through these sequentially, I can go from the top to the bottom and just start substituting. So this gives me W expressed in A is equal to CA to P times W expressed in P. So I get CP to A times W expressed in P times, well, that's CQ to P times W expressed in Q, but W expressed in Q is CB to Q times W expressed in B, which means that the product of these three matrices here must be the transformation from B to A, because this is equal to CB to A times W expressed in B. And that takes us to the end of this particular lecture, where we've done both 313 and 321 Euler angles. And now we'll summarize what we did in this lecture. So as a summary, first we defined Euler angles, and then we constructed two commonly used Euler angle sequences. And they were 313 Euler angles and 321 Euler angles. And for both Euler angle sequences, we determined the coordinate transformations and we determined the angular velocity of the rigid body relative to a base reference frame. Now, Euler angles are going to come up again because when we move further into this material, we need rotations in 3 dimensions, and so we're going to have to use Euler angles to be able to describe those rotations, and we'll get to that when we actually start doing 3-dimensional rotations in the future.